In the next 10 seconds, something the size of a city will spin hundreds of times. Emit X-rays strong enough to outshine entire galaxies. And weigh more than the Sun. It's not science fiction. It's a neutron star, one of the most extreme and fascinating objects in the known universe. So, what is a neutron star? And just how massive is it? To understand, we have to go back to the life cycle of stars. Not all stars die peacefully. The fate of a star is written in its mass. Our Sun, for example, will end its life as a white dwarf, slowly cooling over billions of years. But for stars much more massive than the Sun, the end is far more dramatic. A star is a delicate balance, gravity pulls inward, and nuclear fusion pushes outward. But when a massive star runs out of fuel, no more hydrogen, no more helium, it can no longer fight against gravity. The outer layers explode in a supernova. What remains at the core collapses under its own weight. If the original star was between roughly 8 and 25 times the mass of the Sun, the collapse stops just short of becoming a black hole. What's left is a neutron star. A neutron star is what happens when matter is crushed to its absolute limit. Imagine this: take the entire mass of the Sun, over 330,000 times the mass of the Earth, and compress it into a sphere just 20 kilometers across. That's the size of a small city. But the density, beyond comprehension. 1 teaspoon of neutron star material weighs around 4 billion tons. That's more than Mount Everest in your hand. How can that be possible? In a neutron star, gravity is so intense that electrons and protons are forced to combine, creating a sea of neutrons, hence the name. These neutrons are packed together in a quantum state known as neutron degeneracy. It's one of the few forces in the universe strong enough to resist gravitational collapse. The outer crust is solid, a lattice of atomic nuclei, denser than anything found on Earth. Below that lies the superfluid core, a bizarre, frictionless neutron liquid that can conduct electricity and spin indefinitely. Some neutron stars spin incredibly fast, hundreds of times per second. These are called pulsars. Their magnetic fields are trillions of times stronger than Earth's, and as they rotate, they beam out radiation like cosmic lighthouses. If those beams sweep past Earth, we see pulses of radio waves or X-rays at regular intervals, so precise that pulsars have been called nature's most accurate clocks. Then there are magnetars, neutron stars with magnetic fields so intense they can distort atoms and strip electrons from matter at a distance of thousands of kilometers. A single magnetar flare can release more energy in 1/10 of a second than our Sun emits in 100,000 years. Yet despite their power, neutron stars are hard to find. They're small, dark, and distant. But when they collide, as they sometimes do in binary systems, they produce gravitational waves that ripple through space-time itself. We've detected these waves here on Earth, thanks to observatories like LIGO and Virgo. And when two neutron stars merge, they don't just shake the universe. They create gold. Literally. Elements heavier than iron, like gold, platinum, and uranium, are forged in those violent collisions. The gold in your jewelry may have come from the death spiral of two neutron stars billions of years ago. That's not poetry. That's astrophysics. So how massive are neutron stars, really? Typically, they contain between 1.1 and 2.3 solar masses. Any more than that, and not even neutron degeneracy can hold back gravity, and the object collapses into a black hole. But scientists suspect there may be rare hypermassive neutron stars, temporarily stable due to extreme rotation or magnetic fields, that exist on the edge between neutron star and black hole. We're still probing that boundary. It's one of the great frontiers in modern astrophysics. And here's the twist. Despite being small, invisible to the eye, and incredibly rare, neutron stars may be the keys to understanding matter itself. At their core, they contain densities and states of matter that we cannot reproduce in any laboratory. They challenge the limits of quantum mechanics, general relativity, and nuclear physics, all at once. They are laboratories of the impossible, scattered across space. Not just remnants of dead stars, but clues to the deepest laws of nature. If that ignites your curiosity, subscribe for more journeys into the strange and astonishing fabric of the universe. And in the comments, tell us, what do you think lies at the heart of a neutron star? Because in something no bigger than a city, the entire cosmos might be hiding a few of its final secrets.